Hold on to your britches because we're going to do this one quick.
He isn't lying. We want to make sure we get through these examples so you understand how to balance a chemical equation obeying the conservation of mass. Remember, it can't be created or destroyed, but just rearranged, and using our mole coefficients.
Yes. We call this the table tennis method. We're going to see how it's going. But first, you got to know why the heck we're going to balance an equation.
Conservation of matter. I can't lose atoms. We got to keep track. This is a lot like stocking shelves at Wegmans.
Right.
I got to keep track of how many Cheerios, how much Frosted Flakes.
You can't miss anything because otherwise you're disobeying the law of conservation of matter.
So they have to equal.
Mm-hmm.
They have to be the same on both sides. The product and reactant quantities of carbon must be the same.
Right. And everything becomes accurately predictable, and we'll be able to use this in a later lesson to predict the outcomes of reactions. This is an equation that is not balanced, and let me show you how.
Right. So let's count them up. So what we like to do is count up the H's on the left and count up the H's on the right.
I got two.
Got two. And O's, you got
two.
And H's, you got two. And O's, you got one. Boom. So the H's are balanced, but the O's are not. Okay. So we need to teach you what we do to fix this with whole number coefficients. Notice we cannot add subscripts. If we add subscripts, we've changed.
I can't do H2O2 because that's not what we're supposed to make.
This is what we're saying. The only thing we can add is whole number coefficients. Mm-hmm. If you change the subscripts, you've cheated, and then you've changed the equation, so that doesn't count.
Doesn't work that way.
That's why I wrote it in red.
Mm-hmm. Okay. Coefficients must also be in their simplest reduced form if possible. Sometimes people make mistakes and keep going past where they were supposed to, and you'll see at the very end, all the mole coefficients would have a greatest common factor.
Yes. If you can reduce, you must.
You must.
That's it.
So, simple example. First thing you got to do is list the elements involved in that reaction. Like I listed hydrogen and oxygen on that first example.
Yep. I list them I do them just once underneath the thing, But
then I counted how many each element on each side of the reaction was. That's where I distributed my subscripts. I counted my moles out in front, and I figured out there was 2 hydrogens, 2 oxygens, 2 hydrogens, and then 1 oxygen.
Again, using our skills, right? Mm-hmm. And then in order to balance it, what we're going to do is we're going to change the mole coefficient of one particular element to make it come up with the total that we need.
Right. Count, compare, put in a coefficient, and then you're going to repeat.
And then repeat. And recount and repeat.
All the elements are balanced. That 4 steps. Count the elements, compare them to see if they match, change a coefficient, and then repeat the count to see if they match. And you just keep going back around until they do. And that's when you know you have a balanced equation.
And what's nice about this is you don't really think about it as all 4 steps. Once you get good at it and you've done a few, you just kind of do it. And so let's get into one and see what happens.
With polyatomic ions, however, before we get into them, we always keep the polyatomic ion together. Just like in determining if it's synthesis, decomposition, single place, or double replacement, I put one code letter above the polyatomic ion. We do the same thing here. I'm going to keep it as a chunk because that chunk doesn't break up.
Yeah, so
it just gets moved around.
Here, the only trick there is you got to make sure if you see a polyatomic on the reactant side that the same polyatomic is there on the product side. If that's the case, you're good to go.
So let's do this one my way, and then Mr. Milks will show you how he does it.
All right, yeah, cool. So line underneath. He's going to do a line underneath the arrow. Then he's going to list his elements, Ca and O. We notice we have Ca and O on both sides. So he's going to count them up. I got 1 Ca on the left. I got 1 O2 on the left. Good.
1 O2, which means there's 2 O's.
You're right.
That's right.
I said it
2
wrong.
total O atoms.
Yep. And then I have 1 Ca atom and 1 O atom.
They do not match.
Right. And so we need to balance out the one that doesn't match. So I need to what do I need to multiply the 1 O by to get it up to 2? 1 times 2. So this is what you need to religiously do. Put in the coefficient first. Now redistribute and recount. So now Ca becomes 2 and O becomes 2. Good. Now I've balanced the O's, but now in process I've unbalanced the Ca's, but that's okay. I have to multiply the 1 by a 2. So put the 2 in first. Then we need to do this religiously because if you forget to put that 2 in, you just switch that 1 to 2 without changing the coefficient, then you haven't really balanced your equation.
What goes on that blank line in front of O2, Mr.
In
Milks?
chemistry, when we don't have anything, any number, it's 1.
Yeah, so you're going to actually practice putting that 1 in there just to make sure.
I would put the 1 in there because when these show up as multiple choice questions, the Regents' favorite question is, what is the sum of of the coefficients in the properly balanced equation.
And the
So they're going to
answer
make
would
you
be
balance it,
5.
and then if you take up all the coefficients and add them up, it's 5. And guess what? The answer 4 is going to be there, and so you got to get it right. Okay.
Decomposition. Erase. Now, Mr. Milks does the same thing, but he actually lists his elements in line underneath the area.
I do it
Arrow.
like this.
He counts them on both sides. He kind of puts the elements as the net in ping pong,
Yep.
so to speak.
And I count them like this.
And then he counts it that way. So he has 2 moles of phosphorus, 5 moles of oxygen on the reactant side, and 1 mole of phosphorus and 2 moles of oxygen on the product side.
You got good experience balancing these things. Which one should I balance first, the P or the O?
I would balance the I would definitely balance the O first. And the reason why is because the P is by itself, it's a solid element. So no matter what coefficient you need to put there, you can. The O, on the other hand, comes in packages of 2.
If I were to balance the P and just multiply this by 2, I wouldn't change anything.
It wouldn't help much at this point. He's got to get the oxygens to match.
Oh,
So he's got to go
5
to the lowest common factor between 5 and 2.
Yeah, that means 10.
The first number that both 5 and 2 go into. So he's got to come up to 10
So
total oxygens.
I got to multiply the 5 by 2 to get it up to 10.
Absolutely. So he's
let
going
me
to distribute. So
And
now he's got to recount his elements. He doesn't have 2 phosphorus anymore. Now he's got 4. And now he's got 10 oxygens.
All right, cool.
So that gets us to a point where we can start to make moves on the product side for the oxygen.
So now I got to multiply 2 by 5.
Yep, and he's going to distribute that 5 over there. And now he's got 10 oxygens on the product side, which leaves him just to have to figure out how many phosphorus he needs to put in there. And since it doesn't come in packages of 2 or 3 or something weird like that, he can just put what he needs there, and he's good to go. So that's Milk's method. Let's go back to Monaco's method. It's the same
It
thing.
really is the same thing.
It's
I
just
just
a
end up.
different way to
I just end up writing my elements one time, where he writes them twice. It's no big deal.
Here we
And
go.
honestly, neither of us care which way you pick, but we do need to keep the polyatomics together. So I see NO3 on both sides, so I'm just going to write it as a specific element or as a single element. It makes it easier. Trust me. Okay, so now I just count them up. I have 1 Ag on the left side, and I have 1 NO3. I have 1 Ca. I have 1 Ag. I have 2 NO3s and 1 Ca. So let's balance the NO3s and see what happens. I need to multiply the 1 by the 2, redistribute, and recount, because now I just changed 2 things. Okay, good.
Okay, so NO3s are balanced, but AGs are now out of whack. But that's not so hard for me to deal with, because all I got to do is put a 2 up there, changes that AG to 2, and
we're done.
Yeah, we're
Check,
equal.
check.
Check.
They all equal, so this is balanced. But don't forget, in the blank space, what actually goes there is
Yes, the number 1, sir.
the number 1. So the first few times you guys do this during the practice, we want you to put in the 1 for now to make sure that you remember that it is actually a coefficient of 1.
The big freak out, too, is don't let a big, long, scary-looking equation that has polyatomic ions in it scare you away, because they're actually sometimes simpler to balance than the ones that don't have polyatomic ions in it.
No, and it does really just make it easy to keep them together.
So Milksy is going to be doing a
my way.
double replacement that has multiple polyatomic ions in there. So the Na, the nitrate, calcium, and the sulfate are all considered. So far, he's right.
Right, and I got Ca's 1,
Mhm. 2, yep, 2, and
so there's 1.
there you go. So he's got to figure out how to get the Na and the NO3 to balance up to 2.
All right, so I'm going to do NO3 first, because I can just multiply the 1 by 2.
There he
Pick the
goes.
species that has NO3 in it.
And distributed 2 moles out to it. He's going to double that.
2.
And then what?
Done.
He's already done. Like I just
What?
said, don't let a big, scary-looking equation with polyatomic ions in it make you stop in your feet on your tracks, because they can actually be simpler to balance than the simple.
And this really is just a puzzle. So
We got any more? Because we're running out of time.
yes, we did.
Okay.
So
Don't have much
it's a puzzle.
time.
You need some practice. You'll get confident once you do some practice. Remember, we got to be able to count our atoms.
Right.
Keep your polyatomics together. Do it Monaco's way or do it Milks' way. They both work. They're really the same thing.
And if this lecture don't click, I can show you web pages where you can do games on this stuff, and it will click.
Yes.
Okay.
Oh, I like the one where it evens out.
With
It's
the
got the
teeter-totter.
There you go.
All right, I'll see y'all later. I click the button and